Welcome to Chem Academy with Chelsea Y. Eustachio. For today's lesson, we will discuss disturbing equilibrium using the ICE table. Chemical reaction is in equilibrium when the concentrations of the reactants and products are constant. Once a reacting system has reached equilibrium, it remains at equilibrium until it is disturbed by some change of conditions. The guiding principle is known as the Le Chatelier's principle. The three types of changes that can disturb the equilibrium of a reaction are the changes in concentration, changes in pressure or volume, and changes in temperature. So let's consider the system at equilibrium. A plus B and double arrow C plus D. The small letters represent the coefficients of each element. We can calculate the Kc here by this formula. The concentration of C times the concentration of D at equilibrium divided by the equilibrium concentrations of A and B. Q helps us predict the direction of the shift. The formula for Q is also the same as Kc, but the concentrations are not at equilibrium. For this example, the Kc is the equilibrium constant for the system. The Q, on the other hand, is called the reaction quotient. Where it is compared to K to determine the shift. Now let's proceed to the comparison of Q and K. When Q is less than K, the shift would be forward or to the right. When Q is equal to A, the system is at equilibrium. When Q is greater than K, the shift will be to the left or reverse. When more of any reactants or products is added to the system, the value of Q changes. So it is important to compare Q to K to determine the shift of the equilibrium in the direction that consumes some of the added substance, moving the value of Q towards K. The I in ICE table stands for the initial concentrations or pressures for each species in the reaction mixture. C represents the change in the concentrations or pressures for each species as the system moves towards equilibrium. The E represents the equilibrium concentrations or pressures of each species when the system is in a state of equilibrium. In making an ICE table, the quantity should be expressed in terms of molarity or moles per liter. If using Kp, gaseous species must be expressed in appropriate pressure unit. When calculating the reaction quotient or the Q to determine the direction of the reaction shift to establish equilibrium, we need to use the initial quantities. In calculations involving the equilibrium constant, K, we should use the equilibrium quantities. Let's have an example. Some hydrogen and iodine are mixed at 229 degrees Celsius in a 1-liter container. When equilibrium is established, the following concentrations are present. The concentration for HI is equal to 0.490 moles per liter. The concentration of H2 is equal to 0.080 moles per liter. And the concentration of I2 is equal to 0.060 moles per liter. If an additional 0.300 moles of HI is then added, what concentrations will be present when the new equilibrium is established? The given values are the original equilibrium concentrations. To calculate for the reaction constant, we divide the concentration of HI squared by the concentration of H2 times the concentration of I2. So we have these values: 0.490 squared divided by 0.080 times 0.060. which is equivalent to 50. So now we will add the 0.300 moles of HI to the 1 liter container. Thus, the 0.490 moles per liter concentration of the HI will be added 0.300 moles per liter, which will be equivalent to 0.790 moles per liter. The concentrations of H2 and I2 would not be changed because no moles per liter of those substances are added. H2 is still 0.08 moles per liter, I2 is equal to 0.06 moles per liter, and the concentration of HI changed from 0.49 moles per liter to 0.79 moles per liter. With these initial concentrations, we can compute for the value of Q. Q is equal to the concentration of HI squared divided by the concentrations of H2 and I2. The values are then plugged in, which lead us to the value of Q, which is equal to 130. Because Q is greater than Kc, the reaction proceeds to the left to establish a new equilibrium. The new equilibrium concentrations can be determined as follows. Since the reaction proceeds to the left, we should add moles per liter to the substances at the left and subtract moles per liter from the substances at the right. Since HI has a coefficient of 2, we will subtract 2x, and for H2 and I2, we will add x. Remember, same sides, same sign. And now we have the new equilibrium, wherein H2 is 0.080 plus x, I2 is equal to 0.060 plus x, and the HI is equal to 0.790 minus 2x. Substitution of these values into Kc allows us to evaluate and solve for x. Kc is equal to 50, then we plug in the values, then simplify it, and cross-multiply it to 50. Then we will proceed to the final equation, which is 46x squared plus 10.2x minus 0.38 equals to 0. Then input it in the calculator. Solving this quadratic formula gives us the value of the first x, which is 0.032, and the second x is equal to negative 0.25. Clearly, negative 0.25 is an extraneous root, and because x cannot be less than 0 or cannot be negative, this value would not be used. Thus, the value of x is equal to 0.032, which is the root with physical meaning. So the equilibrium concentrations are computed with this value of x. The concentration of H2 is equal to 0.080 plus x, and the concentration of I2 is equal to 0.060 plus x. The concentration of HI is equal to 0.790 minus 2x. So we plug in the value of x there. So the final concentration of H2 is equal to 0.112 moles per liter. The final concentration for I2 is equal to 0.092 moles per liter. The final concentration for HI is equal to 0.726 moles per liter. Thank you for listening and watching. If you like this video, give this a thumbs up and please subscribe.